Welcome back. In the last session, we were talking about the system stability, right? Then I explained clearly a point when people say one pole system, two pole system, three pole system, etc. that is associated to open loop systems number of poles. Therefore, when I say open loop systems number of poles with unity gain feedback, that is what we consider in control systems. Remember, practically you may have H of S, then we have to consider which is unity gain feedback system, then just put that H of S into your G of S, then effectively that will become loop gain. Therefore, when I say one pole, loop gain pole. When I say two poles, loop gain two poles. Three poles, loop gain three poles, which is having unity gain feedback system. And then we had seen, if you consider one pole system, right, then we have got the root locus, and then we got that system is always stable. Similarly, if you consider the two pole system, therefore if you consider two pole system, tell me, is two pole system always stable according to your understanding? When I say two pole, loop gain two poles, okay, two pole system, then again let us say there are two poles, right? Then let us say G of S is equal to K by S plus A into S plus B. Now we have two poles, right? This is what is, let us say, minus A minus B, or pole P1 P2, anything is fine. Now see, always the poles should be left half of the S plane. I am not going to those details why the poles should be in the left half of the S plane and all, right? Therefore the poles always should be in the left half of the S plane. If they are entering into right half of the S plane, the system is not stable for those poles, for those conditions. Now two pole system, then when K is varying from minimum to maximum, then if you draw the closed loop transfer function or the closed loop system poles, all those poles should be located in the left half of the S plane. Then when you draw root locus, we have the poles will be moving and there is a breakaway point with angle of 90 degrees. Therefore this is what your root locus. Whatever it may be, for any value of K which is from 0 to infinity or minimum to maximum, remember all the poles of closed loop system located in the left half of the S plane. Therefore I can say system is always stable. Therefore system is always stable. Therefore two pole system is always stable. Therefore system is always stable. Two pole system is always stable. Now let us consider three pole system. If you consider three poles, for three pole system, now let us say we have three poles, 1, 2, 3. Let us say G of S is equal to K by S plus A, S plus B, S plus C. Okay. Now if you say minus A minus B minus C, then when K is varying from minimum to maximum, then if you ask the poles, then I think the poles will be going like this, and here the poles will come like this, but there is a breakaway point, then you may get like this. For some values of K, some of the poles are entering into right half of the S plane. Therefore for not all values of K, your system is stable. For not all values of K, your system is stable. System is not completely stable, or people say system is not always stable. It is not always stable. It is stable for few values of K. Let us say K is equal to 0, 0, 0. When K is varying the poles, the pole 1, pole 2, pole 3. Pole 3 is going like this, that is always in the left half of the S plane. And then pole 1, pole 2, because the pole 1, pole 2, right? Therefore pole 1, pole 2 are coming together and then having breakaway point, the pole 1, pole 2, then both the poles are entering into right half of the S plane. Therefore system is becoming unstable for few values of K. Therefore this is what is called system is not always stable. Therefore it is not always stable. Not always stable. If it is not always stable, people consider it as not stable. Therefore system is not stable. Now enough. Maybe if you take four poles, system is not always stable. 5 poles, system is not always stable. Therefore, the observation is the system which is what is having more than 2 poles or more than or equal to 3 poles, that system is not always stable. May be stable, may not be stable. That depends on the value of K. Here basically what is the meaning of K? If you speak with respect to your amplifier, K is nothing but your gain, DC gain or low frequency gain from. If you take differential amplifier, whatever gain you got, right, that is what your loop gain, or which is mid-band gain which we got in the RC coupled C amplifier. Whatever AC parameters we calculated, that is what is your K. We know that the K is varying, right? That time I already told, K is not stable. K is nothing but your DC gain or low frequency gain. If that is what is varying, right, and then the poles are because of what? The internal capacitance or parasitic capacitance or the load capacitance, whatever you have for any system, that is what as an output impedance of the system, and the load of your the load cap of your system will give you a pole. RC combination will give you a pole. Therefore, how many poles are there from input to output, that is depending on the number of stages what you have, then that is what is defining number of poles. Okay, that is fine. Therefore, system is stable or not stable. Everyone understood? Okay, this is what is the observation. Then I will apply this to your op-amp. Then I can say, then we will do some compensation to op-amp to make it completely stable. Okay, that is what. You take it. I'll give you 30 more seconds, then I can say this is done. Therefore, what is the observation? Observation is if number of poles greater than 2, if number of poles greater than 2, then system is, people call it as system is not always stable or unstable. Therefore, remember the total number of poles should be what? The total number of poles should be less than or equal to 2. Okay. Therefore, total number of poles should be less than or equal to 2 for a stable system. Both are same, but this is what is ultimately the conclusion. That is observation and this is conclusion. If you have the total number of poles in the closed loop transfer function, right, less than or equal to 2, then it is always stable. More than 2, not stable. That is the observation. Okay. There is something called marginally stable. That part I will explain from oscillators. Okay. Because your oscillator circuit is marginally stable circuit. That is what is critically damped oscillation, etc., or sustained oscillations. Where gain margin is equal to 0, phase margin is equal to 0. Done. Okay. Now, therefore tell me, is op-amp stable always? The open loop op-amp. The open loop op-amp is always stable. Now, just listen. Right? Again, I need to go back, but anyway, to write down. This is the one, Darlington pair. So many times I am drawing the same block diagram. Now, the first stage, Darlington pair. Okay? And this is also Darlington pair. We are trying to find how many poles are there for open loop op-amp. Okay? Based on that we can say. And now, after this, differential amplifier, diff amp, okay, then common emitter amplifier, CE amplifier, then finally the buffer amplifier or CC amplifier, buffer amplifier. Now this is what is our output V0, and now this is V1. And let me tell you one more point, each stage will contribute a pole. Each stage will contribute a pole. Why each stage will contribute a pole? The reason to have pole is nothing but R and C combination, right? If you have RC, right, or parallel RC or series RC, whatever it may be, then you will get a pole. Now tell me, Darlington pair, it has some output impedance, right? I'm just trying to define. This is parallel, therefore one pole, second pole, third pole, fourth pole, right? But I can say the dominant poles are coming from only differential amplifier and common emitter amplifier. The pole whatever you get from buffer amplifier, the pole whatever you get from Darlington pair can be neglected. Why? Tell me. Therefore each stage, therefore this is all having some cap. Each stage is having some capacitance. This is also having some capacitance, right? And this is also having some capacitance. Let me call this capacitance as C1, because this is what is the gain stage AV1, this is what is gain stage AV2, okay, and this is what, let me call this as C2, okay. Then this is also having some cap, okay. Now what is the gain of this? AV is approximately equal to 1. Here also the AV is approximately equal to 1. But now let me tell, therefore whatever C you have, the CL, right, whatever C you have, here also some C, let us say the load cap, some cap, CL. Now what is the output impedance? This is what is having some output impedance, right? This is what is R0, this is also having some R0. Now your amplifier is also having some R0. That output impedance and the capacitance will create a pole which is 1 by RC, because what is, it is nothing but a low pass filter. If it is a low pass filter, 1 by 2 pi RC, right? Therefore if you write in radians per second instead of hertz, then RC, R0 into C1 is a pole. Similarly it is also having, instead of R0, let me say this is R1, output impedance of stage 1. Stage 1 in the sense the gain stage 1, then R2, okay, and this is what is having output impedance R0. Now tell me, I want to locate the poles which are there in the left half of the S plane. Therefore now tell me, we have a pole, right? The pole from this. Tell me what is the value of R0. If you take Darlington pair, what is the value of R0? The value of R0 is almost 0. Can I say that? Output impedance of Darlington pair or output impedance of your CC amplifier. is almost 0. 20 ohm, 30 ohm, 40 ohm. It is almost 0. If it is almost 0, if R0 is almost 0, if this is almost 0, then tell me the poles which are coming due to the Darlington pair and then buffer amplifier. R into C, R0 into CL. Therefore, R0 into CL, therefore because R is very small, because the pole, now if you ask me the pole, here the pole, right, what is the pole here? Let us say the pole is nothing but 1 by R0 into CL. Because R0 is very less, then what is your pole? Your pole is at infinity. Let us say this is what your pole P1. What is P1? 1 by R1 C1. And what is pole P2? This is 1 by R2 C2. Then what is the pole here? The pole of CC amplifier, right? The first CC amplifier is 1 by R0 CL. Okay? Therefore now tell me, here pole of what? Pole of Darlington pair. Pole of Darlington pair. Okay? Therefore 1 by R0 CL. What is R0 of Darlington pair? Very low. When R0 is very low, when R0 is 0, then what is your pole? Your pole is at infinity. Similarly, if R0 is 0, then your pole is at infinity. These poles are called non-dominant pole. The total system's response is not dictated by these poles. The total system's response is dictated by pole 1, pole 2, because R1 is not 0. R1 is high, R2 is high. Therefore, the poles are nearer to origin. Therefore, now if you ask me the pole locations, the poles whatever you have, the two poles, therefore the pole which is nothing but due to Darlington pair, then the pole due to the CC amplifier will be here. These poles are called non-dominant poles. These poles are called non-dominant poles. Okay. Now then P1, P2, your R1, R2 almost same, and then C1, C2 if you take almost same, the poles whatever you have, P1 and then P2, they will be here only, P1 and P2. These are all nothing but dominant poles. Therefore, these poles are dominant poles. The poles which are nearer to origin, they are called dominant poles. Why? The total system's response is dominated by the poles which are nearer to origin. Therefore, these two are dominant poles. Therefore, now tell me, if I ignore non-dominant poles due to the Darlington pair and the buffer amplifier, only the poles what you have due to gain stages, differential amplifier and the common amplifier, AV1 and then AV2, those poles are dominant poles. Therefore, now tell me, if you take your Opamp is having effectively two poles. Therefore, that is what your open loop system. If you use your Opamp as an open loop system with unity gain feedback, or the feedback which is not having any poles, then your Opamp, whatever Opamp you considered now, is always stable because it is two poles. If the feedback is not having any pole, then your Opamp is always stable, right? But what is the guarantee that you will not have any pole in the feedback? Let us say integrator. Then definitely you will have a pole in the feedback. Then your Opamp is having two poles. Your beta network, whatever you are going to connect to the Opamp in the feedback, is having one more pole. Then total number of poles for a loop gain to consider as unity gain feedback system is equal to 3. 3-pole system is not always stable. Therefore, the Opamp, which is what is having number of stages, effective number of stages, only 2 poles, and the feedback, whatever you are going to connect to your Opamp, let us say integrator, then you have a pole in the feedback, then that is another pole, that is H of S, is having one more pole. Open loop G of S is having 2 poles, 1 pole, effectively 3 poles in the loop gain. 3-pole system is not always stable. Therefore, the system whatever you are developing using Opamp is not always stable. Now tell me, can I increase number of stages whatever I want to improve the gain? Because I told you right from circuit side, AV1, AV2, AV3, you take one more CE amplifier, you will get 3 poles. Then 3-pole system is not always stable. 3-pole system is not always stable. Therefore, don't increase number of stages unless there is a requirement and if you don't want stability. Here the gain, which is, let us say 400 into 500, I am speaking with respect to op-amp, 400 into 500, that is 2 lakhs, more than enough. Therefore 2 stages gain, more than enough. You can take it as infinity, but 2-pole system, but your op-amp is not always stable if you have a pole in the feedback. Then what to do? If you want to have, or if you want to allow at least 1 pole in the feedback of your op-amp, I want to have only 1 pole from your op-amp. What do you mean by having 1 pole? Only differential amplifier. If you have only differential amplifier, remove CE amplifier, then it will become 1-pole system. But what will be your voltage gain or differential gain? Your differential gain will be 400. 400 is not enough. The fundamental requirement of your generic amplifier is to have maximum voltage gain. At least I need 2 stages. I cannot decrease more than 2 stages. Then what to do? I need 2 stages, but I want only 1 pole. I want effectively 1 pole, or I want 1 dominant pole. I want only 1 dominant pole. That is the reason why people are going for op-amp compensation. Therefore, if you ask me, this is nothing but op-amp without compensation. Therefore, this is nothing but op-amp without compensation. If you ask me the frequency response of this, right? The frequency response of this, because there are 2 poles, the frequency response of this, if you ask me the frequency response of your open loop amplifier, there are 2 poles, then until then, your gain is high, but there are 2 poles, Bode plot basically. Now the slope is minus 40 dB per decade, because there are 2 poles, P1 and P2, right? And your gain, let us say this is what is 2 into 10 to the power of 5, and this is what is our mod AD, the differential gain. Different AD itself is magnitude, okay, that's fine. Therefore this is what your AD, okay, take it, and this is not always stable. Therefore observation is op-amp without compensation is having 2 poles. So it is not always stable if feedback network, if beta network contains a pole, hence we need single pole op-amp, we need single dominant pole op-amp, To get single dominant pole op-amp, what to do? That is what is the solution. I think now I explained the problem statement, right? What is the problem statement? The op-amp without any compensation. If you think like stages, stage 1, stage 2, stage 3, stage 4, therefore you have very good voltage gain, very high input impedance, very low output impedance. Those are all fine. The AC parameters are fine. But I am speaking with respect to system stability, because they are going to use this op-amp in the application. Then when you use that op-amp, whatever you are designing and you are releasing into market, which is generic circuit, therefore anybody can take the generic circuit and then get their own circuits. That is what is the application of your op-amp. Then after generating their own or their custom circuits, remember that should be stable. But if your op-amp without any compensation, right, if the feedback is having a pole, then that is not always stable. Okay, therefore we need to have compensation. Therefore how to make it stable, or how to make it single dominant pole, then let's see. That is nothing but your compensation. That part I will explain. Okay, take it. Let me have some water. There are few bits associated to the dominant pole and non-dominant pole, but not like more number of problems, but few problems are there. We don't want to leave anything, right? And not only, see, the concepts whatever we are studying, it's not only to solve the problems. It is to understand, it is to gain the knowledge, and that is to apply later into your career, okay? It's not always GATE examination or IAS examination or public sector unit examinations. No. That is to measure your quality, how much you understand and how much you know. But ultimately, how much you understand, self-motivation, that you need to apply into your career. Therefore, you will excel in your career. That is the ultimate point, not only for the marks. Marks you get automatically. That is secondary. Primary is always knowledge. According to Bode plot, if there is a pole, you'll get minus 20 dB per decade. If there are 2 poles, you'll get minus 40 dB per decade. 3 poles, minus 60 dB per decade. Okay? Pole is nothing but 3 dB frequency. Or I can say the cutoff frequency. Now, write down next topic. Opamp with compensation. Next subheading, Opamp with compensation. You need to draw this again, I guess. The block diagram. Okay? Write down Opamp with compensation. Opamp with compensation. Now, you know what is that? With compensation is nothing but adding compensation capacitor. That's it. I'm just explaining the first cut. Enough for you, for your understanding. Therefore, now we have compensation capacitor. This is CC, compensation capacitor. Right? In between output to input of second stage. That is what is serving you the purpose of stabilizing your op-amp or making dominant pole system. Okay, and it will become dominant pole op-amp. How it is becoming dominant pole op-amp, I will explain. Okay, first of all, draw this, then I'll explain. Now your pole P1, that is earlier. Now the new pole you'll get. Here also you'll get kind of different pole. Okay, because of this. These poles are non-dominant poles, right? This is non-dominant and This is also non-dominant. Only the dominant poles are due to this. But when you add CC in between output to input, what will happen? See, in control systems, we study something called lead compensation, lag compensation, right? One of the compensations. But I am speaking with respect to circuit. Okay. If you draw multiple times, you will remember. Okay. Don't feel bad. Draw it once again. What is the heading? Opamp with compensation. In bracket, dominant pole system. But how it is becoming dominant pole, I will explain. See, now I am going to apply Miller's theorem. That's why we derived Miller's theorem. If I don't explain Miller's theorem, and then if I take that this capacitance can be equivalently represented here, this capacitance equivalently can be represented here, if I explain directly, you will not understand. That's why I derived Miller's theorem first, then we went to the op-amp stability. Okay, just write down. I'll give you 1 minute time. In that time, you try to write. Over? Okay, now let us apply Miller's theorem. Okay, if you apply Miller's theorem, right? What is Miller's theorem? I'm just taking it back. Miller's theorem. If you have any stage, right, A, then input and then output, if there is Z, this is Z, then this is your output and then input, this is equivalently represented as, this is nothing but what? This is equivalently represented this is equivalently represented as this is nothing but Z2 is equal to Z divided by 1 minus 1 by A, and here we can represent Z1 is equal to Z divided by 1 minus A, right? Now if I apply the same thing, right, now this is what is our common emitter amplifier having gain AB2, therefore this is your CE amplifier having gain, let us say AB2, right, then this is what is having the capacitance C or CC, then how will you represent? This is what is equivalently represented as CE amplifier having the gain AB2. Now tell me, let me say this is C1, sorry, this is C1 and this is C2. Therefore what is C1? C1 is nothing but Z1. Let us say what is Z1? Z1 is equal to Z divided by 1 minus A. Tell me, we know that your common emitter amplifier is having gain negative. Okay, then 1 minus of minus positive. Then can I say, right, this is AV2. Then can I say this is nothing but Z divided by 1 plus mod AV2. 1 plus mod AV2. Right? And AV2 is 500. Let us say this is 400, this is 500. Open loop gain, right? 500. 1 plus 500. Approximately 500. Therefore, this is what is Z divided by, you can neglect 1, then mod AV2. Right? Then what is Z? Z is nothing but what? 1 by SCC. That is what is Z. Then what is this? This is nothing but 1 by S into CC into AV2, right? Therefore, AV2, which is magnitude, into CC, right? Which is basically the new cap what you have, which is coming. Therefore, that is nothing but your 1 by SC1. That is what your C1. Similarly, what is Z2? Z2 is equal to Z divided by 1 minus 1 by AV2. What is AV2 if you take it, right? This is nothing but what? Z divided by 1 plus 1 by mod AV2. AV2 is 500. 1 by 500. That can be negated with respect to 1. And this is approximately equal to Z. Therefore, this is nothing but Z. What is Z? 1 by SCC. Therefore, what is this? 1 by SC2. What is C2? CC. Therefore, what is C1? What is C1? C1 is nothing but your gain mod AV2 into CC. What is C2? That is nothing but CC. Therefore, what did you get? If you ask me, when I say C1, C1 is nothing but at the input port, and C2 is nothing but at the output port. Okay, don't confuse with this C1 and that C1. Okay, I mean C1, C2, whatever you have. Maybe you'll have confusion. Do not have the confusion. Let me say this is what is. This is Ci and this is C0, CO. Therefore, this is Ci, and this is CO. Okay, just do not have any confusion with respect to C1, C2. Okay, therefore now what happened? The compensation capacitor, whatever you have for the second gain stage, if you apply Miller's theorem, that is equivalently adding a capacitor at the first stage of your differential amplifier output, which is second stage gain into CC. That is what we are adding here. Similarly, what is the cap which we are adding the Miller capacitor almost at the output stage is nothing but as it is CC. Now tell me what will be your new, or I can say if you take only differential amplifier, I am just drawing this portion. If you take differential amplifier, this is your differential amplifier, right? Then now this is what is our single stage amplifier. This is your CE amplifier. Okay, now already we have what? Therefore now what are we getting here? We are getting second stage gain AV2 into CC, and here we are getting the Miller compensation just to CC. But we have something called, already we have C1, here already we have C2, right? And this is what your gain stage AV1, this is gain stage AV2. Therefore now, and it has output impedance, let us say the output impedance is R1, then this is also having output impedance R2. Therefore, now tell me, what is your pole? Now your pole P1 is equal to 1 by R1. What is your effective capacitance now? Your effective capacitance is C1 plus AV2 into CC. Your capacitance at the first stage output is increased by second gain stage. See, you may say directly, why don't we add cap here? If you add cap here, done. But how much cap we need to add? 500 times of CC. If you add, you will get it. But instead of that, just add CC in between. then automatically it will be effectively 500 times of Cc. Then 500 times of Cc effectively is coming at the input stage. Sorry, at the first stage output. Therefore, this is nothing but your effective cap, which is C1 star, where C1 star is nothing but, therefore, C1 star is nothing but C1 plus mod AV2 into Cc. Similarly, what is your pole P2? Your pole P2 is equal to 1 by R2 into, let us say, C2 star. Then what is our C2 star? C2 star is equal to Cc plus C2. You can take it approximately, the second pole is not changing much, but when you compare with P1, your C1 is changing too much. Therefore, here 500 times of Cc we are adding, only one time of Cc we are adding, the change in P2 can be neglected with respect to the change of P1. Then you know, your C1 is increasing like anything. When C1 is increasing like anything, then your pole P1 will decrease like anything. Then the pole P1 will move towards origin. Then there is a split of P1 to P2. This is what people call it as pole splitting. This is what people call it as pole splitting. Then your pole, the first stage, the first gain stage, pole is becoming dominant pole. Then the complete system's response is dominated by your differential amplifier output pole. Everybody got it? Now it is becoming one pole system. Why it is becoming one pole system? I'll explain with respect to frequency response. Therefore, you'll understand. Okay? You take it. Then I'll explain the frequency response of compensated op-amp. Then you will see. And it will go to almost close to 0. Over? Okay. Now write down frequency response analysis. Sorry, the frequency, the Bode plot. The Bode plot of compensated op-amp. With this, op-amp is over. Then we can go for applications. Okay. So for now, tell me, first of all, root locus, then I'll give you Bode plot. Okay. Root locus, in other words, we have P1 and P2, right? We have P1 and then P2. Now you know the non-dominant poles. I'm not representing. You know, now your P1 is moving towards origin. P1 is moving towards origin. That is what is becoming non-dominant pole, right? And if you ask me the frequency response of your compensated op-amp, right? Frequency response is and this is what your pole because of dominant pole. You know the pole, that pole is 5 Hz for your IC741 op-amp, and the gain whatever you have, which is AB1 into AB2. If you take AB1, AB2 as DC gains, 2 into 10 to the power of 5. This is what your DC gain, and this is what is our AD, the differential gain AD. And maybe this is what is called unity gain frequency. Unity gain frequency. This is 1 MHz. If your second pole and the slope is minus 20 dB per decade. Okay. If the slope, because only one pole is there, then let us say our second pole is here, then I don't bother, right? Why? The slope will decrease minus 40 dB per decade, but if it is after unity gain frequency, I don't bother. Therefore, we need to compensate, or we need to have the second pole after unity gain frequency. Therefore, now this is what is dominant pole system. Your op-amp is now compensated op-amp. Compensated op-amp. Compensated op-amp is dominant pole system. Dominant single pole system. Single pole system. Therefore, it is always stable. Okay. Time is almost done for the session. I think you have 1 minute. Therefore, if you can pause the video, or maybe I'll continue the same thing in the next session, which is the continuation part. Then I'll give you time to write down. Okay. I hope everybody understood, right? Thank you.